Hi there. An important concept in covalent bonding is, as you might know, that the valence electrons of the bonding atoms share the space between the two nuclei. In covalent bonding, as the atoms move closer, the distance between the two nuclei progressively decreases. Each nuclei starts to attract the valence electron of the other nuclei until the attractive forces of the center proton with the negative electron balances the repulsive forces between the two nuclei. At some distance, there is a maximum attractive force between the two nuclei. At this point, we have a covalent bond. The distance between the nuclei is the bond length. In covalent bonding, each atom achieves a full outer level electrons. The valence electrons are shared between the two nuclei, and the shared pair fills the outer level of both nuclei. So even if atom A has one electron and atom B has only one electron, once they form a bond, the pair of electrons will be shared between the two atoms. So this pair of electrons here will fill the outer shell of atom A and at the same time fill the outer shell of atom B. Only the unpaired electrons will take part in forming a covalent bond. The valence electrons are shared between the two nuclei, as I've shown here. Let's just consider one group of atoms, the halogens. As you go down the group, the atomic size increases, so it makes sense that the bond length should increase as the size of the atom increases. A very simplistic view of how covalent bonds are formed. In the first one, where the two hydrogen atoms are brought closer together, the s orbitals of the hydrogen atom will overlap to form a hydrogen molecule, and here we are showing the electrons from each hydrogen forming a pair, and this pair fills the valence shell of both the hydrogen atoms. Now consider hydrogen bonding with fluorine. Fluorine has a p orbital in the second energy level with one electron which is not paired, and of course the hydrogen in the s orbital has an electron that is not paired, and as the two nuclei, the fluorine and the hydrogen nuclei, are brought together, very simply we're showing that the p orbital is overlapping with the s orbital, and both these unpaired electrons occupy the overlap region. Finally, two fluorine atoms brought together to make a fluorine molecule. Again, both the fluorine atoms have unpaired electrons in the p orbital, and a very simplistic view showing that the p orbital is overlapping and the unpaired electrons from each of the fluorine atoms occupying the overlap region, holding the two nuclei together in a molecule. We will later see that this is a very simplistic view, and we will develop this understanding further. So I did say it was a very simplistic view of looking at how the orbitals overlap. In fact, what really happens is before any bonding can take place or any orbitals can overlap to form a covalent bond, the orbitals mix, or there is a concept called hybridization. Here, let's say that an s orbital mixes with p orbital. One s and one p orbital will make a total of two hybrid orbitals. One s plus one p will give you two hybrid orbitals, and it's named sp. So here I'm showing two hybrid orbitals. If this is the central atom, the orbital overlap is no longer a p orbital, but it's actually an sp hybrid orbital. Let's go ahead and look at an example. If you look at beryllium, for example, and you did the electron configuration of beryllium atom, you will find that its electron configuration is simply 2s2. But you also know that in the second energy level, there's some p orbitals available. If you think about beryllium, for example, you would predict that beryllium does not form any bonds at all, but in fact we do know that beryllium chloride does exist. And we also know that under certain conditions, beryllium chloride is a covalent bond. So what really happens is that the 1s orbital, which is this 1s orbital, will pick up one of the p orbitals and create a brand new hybrid orbital. And quantum mechanical calculations tell us that the hybridized orbital has a lower energy than the individual orbitals. So it makes sense to actually use the hybrid orbitals as an explanation for covalent bonding. So once you have the hybrid orbitals, we have two spots. Now the two electrons of the beryllium atom will be singly occupying an orbital each, rather than sharing an orbital here. This allows the beryllium to form the two covalent bonds. So if you think of this little dot here as the central beryllium, it forms two bonds, and each one of those is sp hybrid, sp. And if we were to overlap it with, say, a p orbital from the chlorine, it will be called spp overlap, if you like. And this kind of bonding has a special name. It's called the sigma bond. So the sp beryllium overlaps with the p orbital of the chlorine. And this is where the p orbital comes from. It's only the central atom that hybridizes, by the way. So up here we have a very nice picture of beryllium plus chlorine, where the beryllium central atom has hybridized, just like I showed you here. And it's an sp from the beryllium overlapping with the p of the chlorine. So we should really look at this diagram here. And this one here is sp p overlap. Let's consider boron now. The electron configuration of boron, at least in the valence shell, is 2s2 and 2p1. So we have a total of 3 electrons here. We also know that in the second energy level, there's more p orbitals available. We have a total of 3 electrons. So it pulls out an empty p orbital and it mixes or hybridizes and forms sp2. So one of the s and 2 p orbitals, they mix to form sp2. And we have a total of 3 hybrid orbitals, which can accommodate the 3 electrons that we have on boron. So 1, 2, 3 here. So rather than boron having 1 unpaired and 2 paired, it now has 3 unpaired, quite capable of forming 3 bonds. And if we are to overlap boron with another atom like fluorine, for example, which is a p overlap, sp2 p overlap. So each one of these bonds is sp2, this is sp2, and this one is sp2. So each one of these are sp2, 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 with boron as the central atom, and it will form a trigonal planar shape with no lone pair electrons surrounding the central boron atom. Next element is carbon. Let's see what happens to carbon. Carbon's electron configuration is 2s2, 2p2, and we have a total of 4 electrons. Common sense will tell you that carbon should only make 2 bonds because there's only 2 unpaired electrons. But data shows that carbon can make 4 bonds. So how does this happen? And the explanation again lies in the ability of the orbitals to hybridize, in other words, mix. So one of the s orbitals and 3 p orbitals can mix, making sp3 hybrid, which gives us a total of 4 orbitals. 1, 2, 3, 4. And now each one of these 4 electrons can occupy one of those orbitals in an unpaired form. So we now have 4 unpaired electrons. This gives carbon the ability to form 4 bonds. Let's just say that it is overlapping with hydrogen as in methane. So we have an sp3s overlap in each one of these cases. This is called sigma bonds. And if each one of these sp3 overlaps with another orbital, making a sigma bond, then we have a tetrahedral shape. Next element is nitrogen. Look at the electron configuration of nitrogen. We have in the valence shell, we have 2s2, 2p3, and we have a total of 5 electrons. Now if we combine the s orbital, the single s orbital, with 3 of the p orbitals, we have 1, 2, 3, 4 orbitals altogether. And putting the 5 electrons back into the 4 hybrid orbitals, we realize that there are 3 unpaired electrons, which gives nitrogen the ability to make 3 sp3 bonds or 3 sp3 sigma bonds. And these 2 electrons right here, which are already paired, will not bond at all. It's not available for bonding. So let's just say in case of ammonia, it's overlapping with the s orbital of the hydrogen. We can say that this bond and this bond and this bond is sp3s overlap, also known as sigma bonds. Our next element is oxygen. Looking at the electron configuration for oxygen, we have 2s2, 2p4. Altogether, we have 6 electrons. So if the s orbital hybridizes with all of the 3 p orbitals, and in the second energy level, we don't have any other orbitals for it to hybridize with. So it cannot pull, say for instance, a d orbital, because we are in the second energy level. So in any case, oxygen has only sp3 hybrid orbitals to play with. And putting electrons back into the hybrid orbitals, we realize that it can only form 2 bonds, because the other 2 hybrid orbitals are filled up with paired electrons. These 2 are not available for bonding, and only this one is available for bonding. So oxygen can only make 2 bonds, and the 2 paired electrons will just give oxygen the bent shape because of the greater repulsion between the 2 paired electrons over the hybrid electrons here. I now want to go to phosphorus. Phosphorus is very interesting because it's in the 3rd energy level. The valence shell is 3s2, 3p3, and we have 5 electrons altogether. But know that in the 3rd energy level, you also have d orbitals. So if it has 5 electrons, unlike oxygen, it can pull out d orbitals so that it can accommodate all 5 electrons. So the 1s, 3p, and 1d gives us altogether 3 plus 1 plus 1 is 5 orbitals altogether, and this is the 5 hybrid orbitals. So this is the sp3d, let's just say hybrid. And if this is the central atom is phosphorus, it can form 5 sp3d bonds. And you could have another overlap here. It could be hydrogen or chlorine or fluorine. In case of hydrogen, you'd want to say it's sp3ds overlap. In case of chlorine, it could be sp3d p overlap, as shown here. Last one, sulfur. Another very exciting atom because it's in the 3rd energy level. Sulfur is 3s2, 3p4, and it has d orbitals available, and it has a total of 6 valence electrons. So with 6 valence electrons, sulfur can hybridize with s and all of the 3 p's, and it can pull out 2 of the d orbitals from the 3rd energy level, and 1s plus 3p plus 2d altogether gives sulfur a total of 3, 4, 5, 6 orbitals. We call it sp3d2 orbital, and it's a hybrid orbital. And now you can see that sulfur has the ability to make 6 bonds, and that's why it has an octahedral shape here. And we define or describe this bond as sp3d2 orbital, or sp3d2 overlapping with, in this case here, the P of the fluorine. Great, that ends my first lecture on covalent bonding, and you have now seen how the covalent bonding is formed. The story is a little bit deeper than simply the orbitals overlapping like I showed you before. Thank you very much. I'll see you in my next video.